Imagine you're holding a piece of paper. Two dots are drawn far apart on that sheet. One represents Earth, the other a distant star. Normally, to get from one dot to the other, you trace a straight line along the sheet. But if you fold the paper so the dots touch and punch a tiny hole through, you've suddenly made a shortcut. That simple classroom trick is the intuitive heart of a wormhole, a passage that connects two distant regions of space, and potentially two different times, more directly than the ordinary space between them. That's why wormholes capture our imagination. They offer a way to travel vast distances without crossing the intermediate space. And the same geometry that makes that possible in principle also opens the door to unusual effects with time. But what's the real physics behind this idea? Are wormholes purely the stuff of science fiction, or are they grounded in solid science? Let's walk through the physics step by step, with examples and plain language analogies, so you can see what's genuinely possible and what remains speculative. First, the idea comes straight from Einstein's theory of gravity. In general relativity, mass and energy tell space how to curve, and curved space tells objects how to move. The equations that describe this relationship, Einstein's field equations, are mathematical rules for how geometry and matter interact. Those equations allow a surprising variety of shapes for spacetime. Among them are solutions that take the form of bridges or tunnels linking different regions. One of the earliest mathematical examples was discovered by Albert Einstein and Nathan Rosen in 1935, and it was later called an Einstein-Rosen bridge. The math showed a connection between two universes, but it turned out to be more of a mathematical curiosity than a usable shortcut. That particular bridge would pinch off too quickly for anything to pass through. That didn't kill the idea. In the 1980s, theoretical physicists like Kip Thorne, Michael Morris, and others asked a sharper question. Could there be wormhole geometries that remain open long enough, and with the right properties, for a traveler to pass through? They sketched out what a traversable wormhole would need to look like. A throat you could travel down without being squashed or stretched apart, and without dropping into an event horizon like that of a black hole. Their work made the idea less like a mathematical curiosity and more like a definable object you could analyze. Here's the catch: to hold a traversable wormhole open, you need matter with very strange properties. In everyday life, matter has positive energy density. People, planets, and stars all increase the curvature of space in a way we can measure. But the wormhole geometry requires the opposite in the throat region. Something with negative energy density as measured by an outside observer. That sounds like magic, and indeed it's one of the main reasons traversable wormholes are speculative. Negative energy can be described loosely as a region where the usual rules about energy and gravity are flipped. So gravity behaves repulsively in just the right way to prevent the throat from collapsing. Before you write that off, remember that negative energy isn't a completely foreign concept in physics. Quantum theory allows strange vacuum effects that can produce regions where the energy density is lower than the ordinary vacuum level. The classic laboratory example is the Casimir effect. If you put two uncharged metal plates very close together in a vacuum, they feel a measurable attractive force. That force can be understood as arising from a change in the quantum fluctuations of the electromagnetic field between the plates, effectively producing a tiny negative energy density relative to the outside. It's a tiny effect, but it's real. So, in principle, quantum physics gives us a hint that exotic energy conditions can occur. Physicists have explored whether quantum effects could create or support wormholes. The general verdict is cautious. While quantum fields can produce negative energy locally and temporarily, the effects are typically extremely small, short-lived, and constrained by deeper rules of the theory that prevent you from piling up arbitrarily large amounts of negative energy in one place. Those rules are formalized in things called quantum inequalities, developed by researchers like Larry Ford and Tom Roman, which put limits on the magnitude and duration of negative energy a quantum field can supply. Another route physicists have taken is to imagine engineering thin shells or special distributions of matter that satisfy the equations. Matt Visser, for example, studied thin-shell wormholes constructed by cutting and pasting pieces of known solutions together and analyzing the matter required to keep the throat open. These are useful theoretical laboratories. They clarify the trade-offs and show exactly what types of stress energy are needed, but they didn't make the exotic matter problem vanish. So far we've sounded like a mixed review. The math allows wormholes. Quantum physics hints negative energy can exist, but the practical obstacles are huge. Let's unpack the main practical challenges a bit more, because they tell you why wormholes remain far from a technology we could use tomorrow. Size and stability. To send a person through a wormhole, the throat must be wide enough and the tidal forces mild enough that the traveler isn't crushed by gravity gradients. For a small throat, say, a meter across, the curvature near the throat is extreme unless enormous amounts of energy are arranged in just the right way. Some back-of-the-envelope estimates show that keeping a human-scale throat open could require amounts of exotic energy comparable to the mass energy of a planet or more. Once you start asking for a throat the size of a spaceship, the energy requirements climb precipitously. That's the root of many numbers you'll see tossed around. You'd need the mass of Jupiter, or as much as the Sun. The exact figure depends sensitively on throat size and the specific wormhole design, but the key point is the scale is astronomical. Stability is another problem. Classical wormhole geometries are often unstable to small perturbations. If any matter or radiation falls in, the throat can start to collapse. The exotic matter required must not only exist, but it must be arranged in a way that resists collapse and prevents horizons from forming. Some proposals explore active stabilization, pumps, fields, or feedback mechanisms that actively counteract instabilities. But these are engineering fantasies until we understand how to produce and control large amounts of the necessary exotic energy. Then there's quantum back reaction. Quantum fields in curved spacetime can feed back on the geometry itself. The energy of quantum fluctuations reacts to curvature and can amplify instabilities, possibly destroying a would-be traversable wormhole. Stephen Hawking once argued informally that such quantum effects might prevent time machines and other causality-violating constructs. This intuition was framed as the chronology protection conjecture. While not a theorem, it's a serious expectation that the laws of physics conspire to prevent macro-scale causal paradoxes. More recently, however, clever calculations have found situations where quantum effects can actually render a wormhole traversable, but these tend to be extremely fine-tuned and work only in special contexts. That last point deserves a closer look because it highlights where research has advanced in surprising ways. There are modern papers that show under certain quantum couplings, two black holes joined by a kind of tunnel could briefly become traversable for low-energy signals. The upshot is subtle. Quantum effects can sometimes open a tunnel that looks classically sealed, but the openings are typically microscopic or last for very short times, and the scenarios often require configurations that are not likely to occur naturally. Still, they tell us the story isn't settled. Quantum gravity, the as-yet incomplete union of quantum mechanics and general relativity, could change the rules. Let's talk about another fascinating connection: entanglement. In 2013, Juan Maldacena and Leonard Susskind proposed a conjecture capturing a deep relationship between wormholes and quantum entanglement, paraphrased as ER equals EPR. ER stands for Einstein-Rosen bridges, wormholes, and EPR refers to Einstein-Podolsky-Rosen pairs, entangled particles. The conjecture suggests that entangled particles might be connected by some sort of non-traversable wormhole at the level of the full quantum gravity description. It's not saying you can send signals through entanglement, you can't, but it hints the microscopic fabric of spacetime and the entanglement patterns of quantum states are tightly linked. This idea has led to rich, speculative work indicating that spacetime geometry could be emergent from quantum information. If that's true, then wormholes are not just oddities of the classical equations. They're connected to the way the universe encodes information at the deepest level. But treating ER equals EPR as a route to building macroscopic traversable tunnels would be a big leap. The conjecture gives conceptual insight rather than an engineering plan. What about natural wormholes? Could the universe already contain tunnels hiding in plain sight? Some researchers have speculated that tiny wormholes might have formed in the early universe, primordial wormholes, and that a population of them might still exist. If sizable enough, such objects could reveal themselves gravitationally, acting like compact masses. They could lens background light in particular ways, or if they accrete matter, they might emit signals that mimic black holes. Observationally, astronomers have searched for exotic lensing signatures and anomalies in gravitational wave signals that might betray a wormhole. So far, there is no convincing evidence. That doesn't rule them out at very small scales or in forms that mimic ordinary objects, but observational science is pushing constraints. The absence of strange lensing events and the excellent agreement between gravitational wave observations and black hole models narrow the room for exotic compact objects. Speaking of gravitational waves, could wormholes be detected through them? In principle, yes. If you were to throw matter into a wormhole or collide two wormhole mouths, the resulting gravitational wave signal would have features different from a black hole merger. People have searched for echoes in the ringed-on phase of gravitational wave events, subtle reverberations that might indicate deviations from the standard black hole picture, but the analyses have been inconclusive or controversial so far. The field is active, though, and as gravitational wave detectors become more sensitive, they will test exotic possibilities more stringently. Another practical angle is experimental analogs, systems that mimic key aspects of curved spacetime in laboratories. These aren't real wormholes, but they allow physicists to test ideas about horizons, Hawking-like radiation, and wave propagation in curved geometries. Examples include water channels, optical waveguides, and Bose-Einstein condensates configured so wave excitations feel an effective geometry with horizons. These tabletop experiments are valuable because they bring abstract ideas into controlled testing grounds. Some metamaterials have been proposed that manipulate light in a way reminiscent of a shortcut through space, and people have made optical devices that mimic the geometry of a wormhole for certain waves. Again, these are analogs. They simulate aspects of the math, not the full gravitational fabric behavior required for real spacetime shortcuts. If you're thinking like an engineer, you'll soon ask, suppose we eventually learn how to create or stabilize a macroscopic wormhole. What would using one look like? Several practical questions arise. How would you get to a mouth? If wormhole mouths sit in different places, you'd need to place them where you can reach them. That's already an unusual requirement. You'd have to create and anchor the mouths in locations that are themselves accessible. What happens at the mouth? The interface where ordinary space joins the throat must be engineered to avoid violent tidal forces. If you simply drop a spaceship on a mismatch of geometries, the stresses could tear it apart. The wormhole design needs gentle geometry near each mouth to let matter pass through intact. Which direction does travel go? In many solutions, moving through a wormhole could instantly change your velocity or orientation relative to a distant observer, because the geometry reroutes how distances and times map. You could leave Earth and arrive around another star with the same local velocity you had upon entering, or with a different one, depending on how the wormhole is embedded in the larger spacetime. That makes navigation non-trivial and would require precise control and mapping of the wormhole's embedding. Could you turn a wormhole into a time machine? If you take a wormhole with mouths at the same time and then move one mouth at relativistic speeds, for example, by flying it at near-light speed and bringing it back, time dilation can make the clocks at the two mouths desynchronize. That difference creates an opportunity. Entering one mouth could lead to exiting at a time before you entered, creating a closed time-like curve, essentially a path that loops back on itself in time. That's where the chronology protection issues kick in. Many calculations suggest a wormhole-based time machine would trigger instabilities, perhaps quantum radiation that grows without bound and destroys the wormhole before paradoxes can form. The deeper question, whether causal paradoxes are forbidden by a law of nature, remains unresolved, but most physicists suspect that some mechanism prevents macroscopic, exploitable time travel. Even setting time travel aside, transporting people through a wormhole would face enormous engineering and safety hurdles. Radiation concentrated in the throat, high-energy particles trapped inside, and unknown quantum effects could all be hazards. Safety would require understanding not only classical spacetime geometry, but the behavior of quantum fields in that geometry. In other words, quantum gravity. We don't have a complete quantum gravity theory yet, although candidates like string theory and loop quantum gravity offer frameworks and toy models. Some proposals in these frameworks hint at microscopic wormhole-like structures at the Planck scale, unimaginably tiny, but extrapolating that physics to macroscopic, traversable tunnels is speculative. Let's return to an intuitive way to think about the exotic matter issue. The energy conditions are a set of expectations in general relativity that encode reasonable behavior for matter. Energy density seen by any observer is non-negative. Light rays focus rather than diverge, and so on. Wormholes violate some of these conditions in their throat region. In everyday experience, you never see negative energy densities. Your coffee has positive energy. The planet does, so anything that violates energy conditions is automatically suspect. Quantum field theory weakens those expectations. It allows small, transient violations in controlled ways, but the familiar idea is that you can't have large, sustained violations without paying a price somewhere else. That's why wormholes tend to require either large amounts of negative energy or clever tricks that shuffle around energy in more subtle ways. One of those clever tricks is to make the throat tiny and quantum in nature, then rely on quantum tunneling or other quantum processes to allow passage for information or particles at microscopic scales. There's an active line of thought that real, macroscopic traversable wormholes might be impossible, but microscopic wormholes, continually created and annihilated at the Planck scale, might be part of the quantum foam, the seething microscopic structure people like John Wheeler imagined. Those would be far too small to transport humans, but they might play a role in the deep quantum structure of spacetime, entanglement, or information transfer in quantum gravity. A related modern development involves constructions where coupling two quantum systems appropriately can produce a traversable channel in the dual gravitational description. In these toy models, researchers have shown that introducing special interactions between two quantum systems that are otherwise entangled can render a wormhole traversable for a brief period. It's a fascinating result because it unites quantum information, entanglement, and geometry, and it provides controlled cases where wormhole-like phenomena can be made traversable without classical exotic matter. However, these setups are highly specific, often require finely tuned quantum states, and correspond to low-dimensional toy universes or special black hole analogs, rather than our 3+1-dimensional cosmos. Still, they hint at mechanisms where quantum processes change what's geometrically possible. From a technological point of view, there are big unknowns about creating exotic matter at the necessary scales and controlling it. Producing negative energy densities in a lab is possible, but tiny, Casimir plates are measured in piconewtons and microscopic separations. Scaling those effects up to macroscopic, sustained distributions would require breakthroughs in quantum field control or entirely new forms of matter not yet observed. The alternative, finding naturally occurring wormholes and learning how to access them, is appealing, but searches so far have come up empty or ambiguous. Let's consider a thought experiment to build intuition about how dangerous or useful wormholes might be. Imagine a wormhole whose two mouths are close together on Earth. Walk through one mouth and pop out the nearby other mouth. You've effectively created a short tunnel across a few meters. That would be neat, but it's not the cosmic shortcut we want. Now imagine placing the mouths at widely separated locations, one in the solar system, the other near a distant star. Suddenly, you could jump across light years. The geometry does the heavy lifting, not acceleration. But how do you move mouths to their desired places? If the mouths can be moved, dragging one mouth at relativistic speed can create temporal offsets due to time dilation, transforming spatial shortcuts into time machines. Moving mouths also changes the global geometry and could introduce stresses that pinch off the throat. The upshot is creating a useful, stable, manipulable wormhole appears to require mastery over both spacetime geometry and exotic matter, mastery far beyond our present capabilities. People often ask whether wormholes would be visible. If a wormhole mouth sits in the cosmos, what would it look like through a telescope? The answer depends on environment. If the mouth sits in empty space and is small, it might be essentially invisible unless a background source of light or matter were lensed by it. The gravitational lensing of a wormhole can be strange. Instead of the smooth, one-on-one lensing you get from a spherical mass like a star, a wormhole can produce multiple images, ring-shaped structures, or brightening patterns that don't match ordinary lenses. If the mouth is embedded in an accretion flow, gas falling into it, it might produce emissions analogous to those from black holes, but with differences that could reveal the throat. Astronomers keep testing data for anomalies, and future telescopes with better resolution and sensitivity might yet flag something odd that points to exotic compact objects. There's another practical issue people sometimes miss. Global topology. A wormhole changes the topology of space. It's not just curvature, it's connecting regions in a way that changes which paths are possible. Topology change in general relativity is a tricky business. Some theorems suggest that changing topology dynamically requires singularities or breakdowns of the classical equations, which again pushes you into the quantum gravity regime. If you want to create a wormhole from ordinary space, you likely need processes that evade classical singularity formation, meaning you must invoke quantum gravity. That loops us back to the big unknown. Without a full theory of quantum gravity, we're guessing about which topology-changing processes are allowed. So where does that leave us? The short answer is, wormholes are a legitimate prediction of the mathematics of general relativity, and quantum physics suggests mechanisms that could violate some classical roadblocks. But turning those mathematical solutions into macroscopic, traversable passages usable by humans faces enormous theoretical and practical hurdles. The need for exotic matter or quantum couplings, stability against perturbations and quantum back reaction, enormous energy requirements, and the absence of any observational evidence so far. None of this means the idea should be shelved. Wormholes are a productive part of theoretical physics. They press us to confront the limits of our models, to invent new tools in quantum field theory in curved spacetime, and to probe deep questions about the relationship between geometry and information. The interplay between entanglement and geometry, the ER equals EPR idea, shows how wormholes have migrated from fancy math to central questions about how space itself emerges from quantum degrees of freedom. Even negative results are useful. They teach us about energy conditions, quantum inequalities, and the ways quantum fields regulate the geometry. Practically speaking, if a civilization were to use wormholes someday, it would likely be a civilization that has mastered quantum matter at large scales and controls energy densities far beyond what we can manage. That civilization would also need deep knowledge of topology and spacetime engineering, essentially a mastery of quantum gravity. The time scale for that could be centuries, millennia, or forever. We simply don't know. From our current vantage point, human travel through macroscopic wormholes remains science fiction. But the theoretical foundations tell a coherent story. The idea is not nonsense. It's constrained, subtle, and a gateway to deep physics. To get a better sense of what would be required technically, it's useful to think about specific wormhole metrics physicists write down. Those metrics are recipes for the shape spacetime must take, They specify how distances and times behave near the throat. Simple models show that the throat needs stress energy that violates what are called the null and weak energy conditions. In plainer terms, light rays passing through the throat behave oppositely to how they behave in ordinary mass distributions. Instead of converging under gravity, they can be pushed apart, which is why exotic matter is necessary. Some metrics are engineered so that the violations are confined to a thin shell around the throat, minimizing the amount of exotic matter. But minimizing in this context still often leaves numbers that are astronomically large. Researchers have also considered rotating wormholes, ones with angular momentum. Rotation complicates the geometry, but can also ease certain constraints and produce ergorgens where interesting energy extraction processes occur, analogous to rotating black holes. However, rotation tends to introduce additional instabilities and engineering headaches. There are also charged wormholes, wormholes in higher dimensional spacetimes, used in string theory toy models, and wormholes threaded by cosmic strings. The theoretical menu is large. Each case highlights different trade-offs, but none has yet provided a simple, realistic blueprint for a human-usable tunnel. An appealing idea is using cosmic strings or other topological defects as building materials. Cosmic strings are hypothetical one-dimensional defects in spacetime that might have formed in the early universe. They carry enormous energy per length and produce conical geometry. Some speculative constructions imagine joining strings or using them to stabilize geometries in exotic ways. Again, the objects themselves are hypothetical and would require energies comparable to grand unified theories to produce naturally. If cosmic strings existed and could be manipulated, new options might open, but that's a big if. If you're thinking ahead to how civilization might someday exploit wormholes for communication, you should also consider holography and the possibility of shortcutting information. Even if you could not send matter through a wormhole, certain quantum processes might allow information to be exchanged in ways that, from a higher-level perspective, look like shortcuts. The aforementioned Gauss-Jafferis wall-type constructions show how coupling two entangled systems can allow signals to traverse what, in the gravitational description, looks like a short wormhole. In principle, that could inspire communication schemes based on quantum resources that mimic geometric shortcuts, even if no macroscopic tunnel exists. Finally, let's briefly consider the cultural and philosophical implications. Wormholes, more than many physics topics, capture our urge to explore and our hope for shortcuts across the universe. They force us to ask what space and time really are, how they're connected to information and matter, and whether the universe allows the sorts of manipulations that science fiction imagines. These are not just whimsical questions. They touch the boundaries of physics. Research into wormholes has already yielded practical payoffs. New techniques in quantum field theory computations, clearer statements of energy conditions and their limitations, and fresh insights into the entanglement geometry connection that informs modern quantum gravity research. With all that in the toolkit, the path forward is a mixture of theoretical probes and observational searches. Theoretically, scientists continue to model wormholes in controlled settings, explore the effects of quantum fields, and search for consistent ways to evade the need for vast amounts of exotic matter. Observationally, astronomers scrutinize lensing events, gravitational waves, and high-energy astrophysical phenomena for anomalies that might hint at exotic objects. Laboratory analogs expand our intuition about wave propagation and horizon-like behavior. Together, these approaches chip away at the unknowns. There are also paths that might suddenly change the picture. A discovery of a new form of matter with stable negative energy density properties. A breakthrough in quantum gravity that shows topology change is easier than expected. Or an observational signature that unmistakably points to an exotic compact object that can only be explained by a wormhole-like geometry. Any of those would be revolutionary. On the flip side, stronger observational constraints and deeper theorems could shut down many of the speculative loopholes and relegate traversable wormholes forever to theoretical curiosities and microscopic quantum features. For now, wormholes remain an elegant consequence of the mathematics of gravity, a provocative bridge to quantum physics, and an inspiring idea for imagining future technologies. They teach us to think differently about space, time, and information, and they keep theoretical physicists honest by presenting tricky problems that probe the foundations of our theories. If you're excited by the idea of harnessing wormholes, the real work is in pushing the frontiers of quantum field theory, general relativity, and experimental astrophysics, and waiting to see whether nature provides surprises we can exploit. Let's dig a bit deeper into a few concrete research results that illustrate how subtle and interesting the subject is. One set of results involves the so-called averaged energy conditions. Classical energy conditions say things like energy density is non-negative everywhere, but quantum fields can violate those conditions locally. The averaged null energy condition, ANEC, softens the demand. Instead of requiring positivity point by point, it requires positivity when averaged along complete light-like paths. In many contexts, ANEC holds and prevents exotic topologies. But clever constructions show that ANEC can be violated in limited ways, creating openings for transient phenomena like brief traversability. The upshot is, even where energy conditions limit what geometry can do classically, quantum theory sometimes finds loopholes, but those loopholes are typically constrained enough that you don't get free lunch. Other papers explore specific wormhole constructions that minimize the exotic matter. For example, you can design geometries where the throat is surrounded by a region whose stress energy is exotic but very small in integrated amount, even if locally it's extreme. These minimum exotic matter constructions are interesting because they map the boundary between allowed and forbidden geometries. They also inspire questions. Could astrophysical processes, say, the collision of compact objects or phase transitions in the early universe, produce configurations with the right profile? So far, there's no strong mechanism, but mapping the landscape helps define observational targets. A particularly tantalizing development is the idea of traversable wormholes created by quantum effects without requiring classical exotic matter in the same sense. In certain low-dimensional toy models or in highly symmetric setups, turning on specific quantum couplings lets information and even small amounts of matter traverse a region that classically would be blocked. These solutions are delicate. They exploit precise correlations and quantum entanglement, and they often require the geometry to be prepared in a special quantum state. Translating those recipes into realistic, three-dimensional astrophysical wormholes is an open challenge. But the results show the repertoire of possibilities is broader than classical thinking suggests. Meanwhile, laboratory analogs continue to teach us about horizon and tunneling physics. One of the most celebrated achievements has been simulating Hawking radiation analogs in Bose-Einstein condensates and optical fibers. Those experiments don't create curved spacetime, but they create conditions where wave excitations behave mathematically like fields near a black hole horizon. They've given empirical support for the notion that quantum fields near horizons produce thermal radiation, reinforcing confidence in the quantum gravity-inspired predictions. If analogs could be extended to mimic aspects of wormhole geometries, they might let us experimentally probe stability properties and wave propagation through throat-like regions. Observationally, several strategies could locate or rule out astrophysical wormholes. Microlensing surveys, especially ones that monitor millions of stars continuously, can detect compact objects passing in front of background stars. The signature of a wormhole could be distinct from a black hole or planet, especially if the lensing produces unusual time-dependent brightness patterns. Similarly, high-resolution imaging of black hole candidates, like the Event Horizon Telescope images, provides a direct window into the near-horizon region. If a putative black hole were actually a wormhole mouth, the shadow and surrounding emission might differ subtly from predictions for a black hole, although disentangling environmental effects from fundamental differences is hard. Gravitational wave detectors are another frontier. Merging objects that are wormhole mouths could produce waveforms distinguishable from black hole mergers, and future detectors with greater sensitivity could pick out such signals if they occur. Finally, searches for fast radio bursts and other transient signals may reveal features tied to exotic compact objects, though many conventional explanations exist for such transients. In terms of timescales, if wormholes are possible, they're more likely to be microscopic footprints of quantum gravity or rare astrophysical relics than convenient cosmic highways for a long time. The energies and control required to create and maintain a macroscopic traversable throat are comparable to controlling planet-scale mass energy, and the theoretical tools needed to design such entities, a complete, tested quantum gravity, remain under development. So the conservative expectation is that wormholes will remain mostly a deep theoretical playground that informs our understanding of the universe, rather than an imminent transport technology. Still, that doesn't mean the story is boring. The questions wormholes raise push us into some of the most exciting corners of modern physics. How does spacetime emerge from quantum degrees of freedom? What constraints do quantum fields impose on geometry? How does information escape or cross horizons? Research motivated by wormholes has already fueled progress in quantum information theory, the study of black hole thermodynamics, and the search for observational fingerprints of exotic compact objects. The cross-fertilization is one reason many physicists find the topic irresistible. It links the mathematical elegance of general relativity to the counterintuitive truth of quantum mechanics, and to the practical realities of astrophysical observation. Next, it's worth looking more closely at the mathematical structure of some simple wormhole models and what those structures imply physically. Consider a symmetric, static throat, a picture often used in popular descriptions. You have two identical regions of space connected by a narrow throat with a minimum radius at the center. If you move away from the center on either side, space flares out to the usual asymptotic regions. The metric that describes distances in such a geometry contains a shape function that encodes how narrow or wide the throat is, and this function determines the tidal forces and the energy requirements. If the shape function changes too sharply, tidal forces spike and any traveler is torn apart. If it changes gently, a traveler could, in principle, pass through safely. The trade-off is the gentleness tends to increase the amount of exotic matter required. Various trade-offs of this kind have been studied: how to minimize exotic matter, how to distribute it, and how to make the geometry as stable as possible. Rotating and charged wormholes add twists, literally, to the story. Rotation produces frame dragging, the twisting of inertial frames, and can allow more complex trajectories through the throat. It can also introduce regions where weird energy extraction processes are possible, similar to the Penrose process around rotating black holes. Charge introduces electromagnetic fields that interact with the gravitational geometry and can modify the stress-energy balance. Both rotation and charge complicate the stability analysis, but broaden the set of possible solutions. The community has also explored more exotic support mechanisms. For instance, in certain higher dimensional theories, or with particular scalar fields, like those appearing in some cosmological models, the need for negative energy can be reduced or replaced by fields with non-standard kinetic terms. These are not standard particles or fields in the standard model, but they show the range of ways theory can bend to accommodate unusual geometries. Of course, speculative fields need experimental evidence before they can be taken as viable engineering tools. From a philosophical perspective, wormholes raise deep questions about locality and causality. If spacetime contains shortcuts that link distant regions non-locally, what does that imply about the fundamental meaning of distance? If entanglement and geometry are connected, then what we thought of as spooky action at a distance in quantum mechanics might be just a reflection of hidden geometric connections. Those ideas don't change how experiments work in the near term, but they reshape our conceptual framework for thinking about space and information. There's one more practical thought experiment that's often useful. Imagine an advanced civilization wants to create an interstellar network of wormholes. How might it proceed? They would need to create or discover a pair of mouths, stabilize each mouth, fix the mouth's relative motion to prevent unwanted time shifts, and shield the path from destructive quantum effects. The mouths would need to be anchored gravitationally or magnetically to avoid drifting, and they'd need active feedback to counter instabilities. That civilization would also need to monitor the throat for hazards like high-energy particle accumulation and have protocols for safe passage. Each of these tasks demands physical control beyond our current capabilities. The engineering picture is daunting, but not logically inconsistent. Given enough control over matter and energy, and a deep understanding of quantum gravity, an interstellar wormhole network is not obviously forbidden by any known conservation law. The challenge is the gap between possibility and practice. All of this leads naturally to the kinds of research that seem most promising for advancing our understanding of wormholes. The first is continued work on semi-classical gravity, solving Einstein's equations with quantum stress energy sources to see how quantum effects shape geometry. That's hard math, but it's the direct way to test whether quantum fields can sustain or destroy candidate wormhole geometries. The second is searching for observational signatures, refining lensing models, mining gravitational wave data, and watching for astrophysical anomalies consistent with exotic compact objects. The third is developing analog experiments to explore wave dynamics and horizon-like phenomena in controlled settings. And the fourth is pushing fundamental theory, understanding how spacetime and entanglement interrelate, probing the ER equals EPR conjecture, and developing concrete models in candidate quantum gravity frameworks that either permit or rule out macroscopic traversable wormholes. As we explore those research directions, it helps to keep a clear distinction in mind between three classes of wormhole-related ideas. First, purely mathematical solutions of classical general relativity that demonstrate logical possibilities but require matter-violating classical energy conditions. Second, semi-classical or quantum scenarios where quantum fields alter the picture in limited ways and sometimes open loopholes under special conditions. Third, speculative but structured ideas from quantum gravity and quantum information theory that point to deeper connections between geometry and entanglement and may eventually change what's possible. Each class has its own standards for evidence and its own practical implications. That refined perspective helps avoid two common pitfalls: wild extrapolation from toy models to reality and premature dismissal of the entire subject as impossible. Wormholes are a fertile testing ground for ideas precisely because they lie at the intersection of many disciplines: relativity, quantum field theory, astrophysics, and quantum information. Whether they turn out to be macroscopic bridges we can cross, tiny quantum features of spacetime, or theoretical tools that illuminate other puzzles, their study pushes physics forward. So when you hear the headline, "Wormholes are real," a good reaction is, yes, in the sense that the equations of physics allow solutions that look like wormholes. No, in the sense that there's no convincing evidence of accessible, traversable wormholes in our universe, and huge engineering and theoretical obstacles remain. The truth is more interesting than either extreme. The mathematics is real and rich, quantum physics offers surprising possibilities, and observational science gives us a clear path to test speculative ideas. The rest of the story, whether wormholes are ever harnessable, depends on discoveries that may lie decades or centuries ahead, or on theoretical breakthroughs that change the game today. Looking forward, there are concrete ways to make progress that could sharpen our picture. High-sensitivity gravitational wave observatories, like the proposed space-based detectors and next-generation ground detectors, will greatly expand the catalog of compact object mergers and could pick up signatures inconsistent with simple black holes. Improved microlensing surveys will continue to test for compact, non-luminous objects. Meanwhile, advances in quantum technologies could allow laboratory demonstrations of information-theoretic analogs to wormhole traversal, illuminating the connection between entanglement and geometric shortcuts. And foundational work in quantum gravity will either provide mechanisms for topology change and macroscopic wormholes, or show why such constructs are forbidden. As we keep probing, one of the most valuable lessons from wormhole research is methodological. We learn to use extreme thought experiments to reveal hidden assumptions in our theories. By asking what if in extreme cases, we discover which principles are robust and which depend on unproven hypotheses. Wormholes are a prime example of how a provocative question can catalyze new understanding even if the original dream, practical, human-sized tunnels through space, remains out of reach for now. With that in mind, the next step is to explore some of the specific mathematical toy models physicists use to test these ideas, and to show through simple examples how tiny quantum loopholes can briefly allow traversal in otherwise sealed geometries. Those examples illuminate the delicate balance between geometry and quantum fields, and they demonstrate why so many bright minds are still drawn to this problem. We left off pointing toward concrete toy models and the surprising ways quantum effects can open tiny windows through otherwise sealed geometry. Let's take that next step carefully, build some simple pictures of how physicists model wormholes, then see how quantum tricks can change the story, and finally look at what those controlled examples teach us about what's possible and what remains fantasy. Start with the kind of wormhole most popular science descriptions use because it's simple to visualize: a symmetric tunnel connecting two faraway regions. Physicists write down a metric for that geometry, basically a recipe that tells you how to measure distances and times in the neighborhood of the tunnel. Two pieces of that recipe matter most for an intuitive picture. One piece controls how the tunnel narrows and widens as you go through the throat. Imagine the neck of an hourglass or the mouth of a cave, and the other piece controls how clocks tick as you approach the throat, whether time stretches or speeds up. If the neck narrows gently and the time behavior is well behaved, a spaceship could cruise through without being spaghettified or crushed. That gentleness requirement is actually where the trouble starts. To make a narrow throat that doesn't pinch closed, the geometry must flare out as you move away from the minimum radius. In normal gravity produced by ordinary matter, gravity focuses things. Light rays tend to converge, and small tubes of space tend to shrink under the attraction. But a wormhole throat needs the opposite locally, a repulsive effect which prevents the tube from collapsing. In the language of general relativity, that means some components of the stress energy, the source of gravity, have to be negative from the point of view of certain observers. In everyday terms, you need something that acts gravitationally like antimass in the throat. That's why the Morris-Thorne wormhole, a concrete, easy-to-analyze model that a lot of popular descriptions use, explicitly builds in an exotic material region confined to the throat. The authors designed the shape of the throat to be traversable and then asked, what stress energy would produce such a shape? The answer was, exotic stress energy violating familiar energy conditions. They framed it as an engineering problem. What are the minimum requirements to make a puppy-passable pipe through space? To make the engineering idea more concrete, many later papers introduced a volume quantifier, a way to integrate the amount of exoticness over a slice of the throat region to estimate how much of that odd matter you need. The encouraging early results showed you could sometimes keep the quantity integrated over space surprisingly small, while keeping the throat large enough for a traveler, at least by some measures. But small here is a relative theoretical concept. When translated into real units, the required exotic mass often still scaled to astronomical values. The bottom line from classical analysis: you can design geometries that limit where exotic matter is needed, but you can't make the requirement vanish entirely without paying a price elsewhere in the equations. Now here's where quantum physics creeps into the story in an unexpectedly hopeful way. Quantum fields do strange things in curved space or in constrained geometries. The Casimir effect is the canonical laboratory example. Put two parallel, conducting plates a hair's breadth apart, and the quantum vacuum between them has less energy than the vacuum outside. That difference shows up as an attractive force between the plates and can be described as a tiny negative energy density in the space between them. The magnitude is tiny and falls off quickly with the plate separation, but it proves the concept. Negative energy densities do occur in nature, at least locally and transiently. Quantum field theory has built-in safeguards, though. If you try to be greedy, accumulate arbitrarily large negative energy for long times, other quantum effects kick in and punish you. These are the quantum inequalities that people like Larry Ford and Tom Roman developed. Rough, general statements that limit how negative energy can be, for how long, and over what region. They're not simple arithmetic formulas you can plug numbers into with ease, but they express the idea that quantum theory allows violations of classical energy rules only in limited pockets and only briefly. In wormhole terms, that suggests quantum matter might open small, short-lived passages, but is unlikely to provide stable, human-scale tunnels without a major breakthrough. Even so, researchers asked a sharper question. Can clever quantum setups do more than tiny, fleeting effects? And the answer that emerged over the last decade is, sometimes yes, but with major caveats. The most striking examples come from a mix of semi-classical gravity, quantum information ideas, and explicit toy models where the math can be carried through cleanly. The basic strategy in these examples is to start with a pair of black holes that are highly entangled, the thermofield double, state in the language of ADS/CFT, which, in the classical picture, are connected by an Einstein-Rosen bridge that's not traversable. Then introduce a small, controlled coupling between the two sides. That coupling changes the stress energy seen by the geometry in a way that can create a narrow window when the throat is briefly traversable for low-energy signals. This construction is often described in the shorthand double trace deformation, or more simply as turning on a small interaction between the two otherwise entangled systems. The physical intuition is reasonably straightforward if you're willing to accept a hand-wavy picture. Entanglement connects the two sides at a deep quantum level, ER equals EPR intuition, but that connection alone doesn't let you send messages. Think of entanglement like a pair of matched locks. They're correlated, but you can't use them to transmit a code unless you exchange information across a classical channel. The coupling acts like that classical channel. It nudges the state so that the quantum correlations become usable for sending a tiny packet of information. In the gravitational description, that nudge corresponds to a slight negative energy perturbation traveling into the throat, and for a brief time, opening the passage enough for a low-energy signal to make it through. A precise calculation along these lines was worked out by researchers including Gao, Jafferis, and Wall. They showed that in certain low-dimensional anti-de Sitter toy universes, a carefully tuned coupling makes the wormhole traversable. The amount of information you can send is proportional to the strength and duration of the coupling, and is small compared to what you'd need to send a macroscopic object. The window during which passage is possible is brief, and the signal must be timed and tuned precisely. Crucially, those constructions do not violate causality. You can send information forward in time across the bridge, but you cannot use the trick to create closed time-like curves or send messages to your own past, at least not without running into other instabilities or quantum backreaction that ruin the setup. People have pushed these ideas forward by studying explicit quantum mechanical models that mimic aspects of black holes and their entanglement structure. The Sachdev-Yekitev (SYK) model, a solvable toy model of many interacting fermions with random couplings, has proven especially useful. When two SYK systems are put into a thermofield double entangled state and then weakly coupled, computations show an effective traversability that mirrors the gravitational picture. A small window appears, and a limited amount of information can be transferred. What's powerful about those results is that they can be carried out in explicit quantum mechanics, not just heuristic gravity arguments. That ties the gravity intuition to solid quantum computations and lends weight to the idea that entanglement plus interaction can mimic what looks like a wormhole connection. Even with these elegant results, the limitations are clear. The traversable channels produced by these quantum tricks are microscopic in information capacity for realistic parameters and rely on highly controlled quantum states that are almost implausible in an astrophysical setting. They require pre-shared entanglement equivalent to that of two near-identical black holes or specially prepared many-body quantum systems. They also require carefully timed coupling. So while they illuminate deep connections among entanglement, geometry, and information, they don't provide a practical blueprint for opening a star-spanning shortcut you can drive a rocket through. Let's unpack the physics of why traversability tends to be tiny. The negative energy needed to open a wormhole throat acts like a narrow, localized shock that cancels the natural focusing of light rays and opens a passage. The amount of negative energy you can get from quantum fields in realistic settings is limited by several factors. The quantum inequalities we already mentioned, the tendency of quantum backreaction to amplify and then destroy instabilities, and the fact that the energy available from entanglement coupling tricks scales slowly with system size. If you want to make the throat wide enough for a human-sized object, you need negative energy integrated over a large volume and for a long time. Precisely, the regime quantum theory forbids us from occupying without paying a price. The toy setups dodge the price by allowing only tiny, well-controlled windows. There's another way to approach wormholes that's insightful because it highlights why topology change, creating a new handle in space, is hard in classical general relativity. Suppose you want to take ordinary space and cut a hole, then sew in a throat. Classical theorems suggest that changing the topology of space in a smooth way usually forces singularities or the breakdown of the classical field equations somewhere in the history of that process. That means if you want to create a wormhole from nothing, you likely have to involve quantum gravity, a regime where spacetime itself is fluctuating massively and the classical picture of geometry doesn't apply. In that picture, wormholes might naturally arise as ephemeral features in the quantum foam, tiny, Planck-scale throats constantly forming and vanishing. These microscopic wormholes could be important for deep conceptual issues, like how information is encoded in spacetime or how entanglement builds geometry, but they're useless for everyday travel. Beyond the toy quantum constructions and the topology change difficulties, people have studied a menagerie of classical and semi-classical wormhole types to see which features are robust and which are artifacts of special assumptions. Some variations reduce the required exotic matter by using higher dimensions, introducing extra fields that do unusual stress-energy things, or exploiting rotation and charge. Others try to confine the exotic matter to a thin shell around the throat, which makes the exotic region as small as possible. Each variant shifts the trade-offs. You can reduce the integrated exoticness if you allow other complications like unstable oscillatory modes, large tidal forces, or the presence of horizons that spoil traversability. Rotation, for instance, complicates the geometry but can also relieve some energy demands in certain directions. A rotating throat drags spacetime along with it, frame dragging, and that effect can alter how geodesics, the paths particles follow, behave near the throat. However, rotation introduces additional instabilities, ergorgens and superradiant modes, that must be handled. Adding electric charge to a wormhole similarly modifies the balance of forces, but brings electromagnetic instabilities and the need to manage additional fields. These are clever engineering knobs on the theoretical side, but none of them provide an easy out of the exotic matter problem. It's also worth noting that much of the wormhole literature probes the limits by asking extreme, clarifying questions. For example, what if you try to thread a wormhole with ordinary matter moving through it? How does the throat react when tidal stresses, electromagnetic fields, or radiation pass? Linear perturbation analyses often show that the throat responds violently. Small perturbations can grow, causing the geometry to collapse or pinch off unless active stabilization is present. That's one of the reasons people talk about pumps or feedback mechanisms in speculative engineering sketches. You'd need active systems constantly adjusting the stress-energy distribution in the throat to counter instabilities. In a full quantum treatment, these pumps would have to be quantum devices too, with their own energy and entropy costs, making the engineering problem even more forbidding. On the observational front, the search for naturally occurring exotic compact objects, things that could be wormhole mouths masquerading as black holes, is active and getting more precise. Astronomers look for three main types of signals. First, gravitational lensing. A wormhole mouth will curve light in peculiar ways. If you have a bright background source, the wormhole's lensing pattern can produce multiple images, rings, or brightness changes that don't match the clean predictions for a normal star or black hole. The details depend on the throat size and the matter distribution nearby. Large surveys that monitor millions of stars for microlensing events could, in principle, pick up anomalies that suggest something exotic. Second, direct imaging of compact objects. The Event Horizon Telescope's image of a black hole shadow gave us our first real glimpse into the near-horizon region of a supermassive compact object. If some candidates are wormhole mouths rather than black holes, their shadows and surrounding emission could differ subtly. For example, a wormhole might lack a true event horizon, which changes the way infalling matter adds light to the image. Disentangling environmental noise, accretion flows, magnetic fields, and plasma effects from fundamental differences in geometry is challenging, but as imaging gets sharper, we'll be able to test models more stringently. Third, gravitational waves. Merging compact objects produce ripples in spacetime with waveforms that are sensitive to the internal structure of the objects. Black holes have a very specific ring-down signature after merger, set by their quasi-normal modes. If you merge something exotic, a pair of wormhole mouths, or a wormhole mouth with a black hole, the post-merger signal may show echoes or deviations from the black hole template. There have been controversial claims of echoes in LIGO/Virgo data. So far, nothing conclusive has been confirmed, but future detectors with greater sensitivity and bandwidth will push these searches far deeper. Those observational avenues are powerful because they don't depend on our speculative ability to build wormholes. If nature hides mouths somewhere, improved telescopes and detectors are our best chance of finding them. So far, observations constrain large populations of exotic objects, but they don't completely rule out rare or small wormholes, or wormholes that mimic black holes closely. There's another fertile line of research that is often underappreciated: laboratory analogs. These are not wormholes in the gravitational sense, but they simulate key mathematical features of propagating waves in curved backgrounds. For instance, metamaterials engineered to have a specific refractive index can guide electromagnetic waves so that the path the waves follow mimics a shortcut between two regions. In one demonstration, researchers built an electromagnetic wormhole that guided magnetic fields between two separated regions of space without much leakage into the surrounding material, effectively hiding the connecting path from external observers. Such devices don't bend spacetime. They control fields in ordinary space to reproduce some effects of curved geometry. Still, they're valuable because they let us test wave propagation, mode conversion, and the effect of throat-like structures on signals in well-controlled laboratory settings. Analog experiments have also simulated aspects of horizon physics and Hawking-like radiation in fluid flows and Bose-Einstein condensates. These analogs sharpen intuition and sometimes reveal surprises about stability and signal dynamics that feed back into gravitational theory. A natural question to ask is whether wormholes and quantum teleportation are related in a practical way. The short answer is related conceptually, but not interchangeable. Quantum teleportation transfers an unknown quantum state from one place to another using a pair of entangled particles and a classical message. Entanglement alone doesn't send information, the classical message does. The traversable wormhole constructions in quantum gravity mirror this architecture. Entanglement sets up the deep quantum connection. Think of the Einstein-Rosen bridge as the geometric shadow of entanglement. And an extra coupling, analogous to the classical channel, is needed to make the entanglement usable for sending signals. Some papers even draw a direct map between a teleportation protocol and sending a message through a traversable wormhole in the dual gravity description. That mapping is beautiful and clarifying. It shows how information-theoretic tasks can have geometric avatars. But it also reinforces why wormholes don't give free information transmission and why they require additional resources. You need both quantum entanglement and a way to coordinate operations across the two sides. The more philosophical implications of this line of work are intriguing. If entanglement patterns can be read as geometric connections, then space itself might be emergent from quantum information. That's the deeper message that ER equals EPR and related investigations hint at. Geometry is not fundamental in the way textbooks often present it. It might be a large-scale bookkeeping of how quantum degrees of freedom are entangled. Wormholes, in that view, are simply extreme examples where entanglement builds a direct channel in the emergent geometry. Whether that perspective leads to practical technology or simply helps us reframe deep theoretical puzzles, it's already reshaping how people think about space, gravity, and information. Returning to the pragmatic physics, what would it realistically take to make a traversable wormhole big enough for a person? The honest answer walks back to the energy scales. Scaling up the tiny quantum effects we can produce in experiments, Casimir plates, squeezed vacuum states, or entanglement-enabled traversable channels in laboratory many-body systems, to macroscopic, long-lived negative energy distributions is wildly beyond our present ability. The Casimir energy between realistic plates gives forces measurable only with delicate apparatuses at micron separations. To get comparable negative energy over cubic meters, you would need materials and field configurations that we neither know how to produce nor have any experimental sign of existing in nature. Physics doesn't rule out exotic forms of matter that could do the job. People have proposed fields with non-standard kinetic terms or hypothetical topological defects. But until such objects are discovered or produced, the chain between microscopic quantum tricks and macroscopic human transport remains broken. That's not to say progress isn't possible or interesting. Mapping the precise ways quantum fields can violate classical energy conditions, refining the quantum inequalities, and building ever more sophisticated toy models are all productive research directions. They illuminate what aspects of our theories are robust and which depend on untested assumptions. At the same time, observational astronomy and gravitational wave science are steadily restricting the parameter space in which large, exotic compact objects could hide. To make this less abstract, consider two very concrete thought experiments that clarify the limits. First, the message through a quantum wormhole experiment. Imagine two laboratories, A and B, each containing a system that together form a thermophile double-like entangled pair. Prepare the entanglement perfectly, and then switch on a weak coupling for a tightly controlled interval. Now send a single low-energy quantum signal into Lab A that is entangled appropriately with the prepared state. The coupling can allow that quantum to re-emerge in Lab B after a short time, the analogy to traversing a wormhole in the dual picture. This is precisely the kind of transfer that SYK-type simulations show is possible. But scale up the signal, try to send a macroscopic object, and the coupling required grows dramatically. The window closes, quantum back reaction becomes important, and the nice behavior disappears. The experiment shows that quantum gravity-inspired traversability is real at microscopic information scales, but staggers when you try to convert it to macroscopic transport. Second, the thin-shell engineered wormhole thought experiment. Suppose you're a master engineer who can cut and paste spacetime. You take two spherical patches of space, cut out holes in them, and glue the holes together with a thin shell of matter whose stress energy you fully control. If you can tune the shell's pressure and tension, you can create a throat that, from the outside, looks like two mouths connected. Matt Visser and others showed how to analyze precisely what the shell must do. You'll find the shell needs negative energy densities or tensions in certain components, the exotic matter again. You can minimize the integrated exotic matter by choosing the shell properties carefully, but you cannot remove the need for something exotic entirely. If you move either mouth or allow ordinary matter to fall in, the shell needs active control to remain stable. This exercise is useful because it turns the problem into an engineering one with clearly defined inputs and outputs, and it makes transparent where the obstacles sit. Exotic stress energy in the shell, sensitivity to perturbations, and the need for active stabilization. Both thought experiments are instructive. They show how controlled manipulations of quantum states or stress energy can produce tiny traversability, and they show why scaling those manipulations to macroscopic sizes is not just a matter of better engineering, but of new physics. Before we go further, and to ground the discussion so it doesn't float off into metaphysics, it's helpful to recap three technical but intuitive rules of thumb that come up repeatedly in wormhole studies. Local violations are easier than global ones. Quantum fields readily produce small, local negative energies, Casimir-type effects. Keeping large regions in a steady negative energy state for long times is what's hard, and what the quantum inequalities forbid or severely constrain. Small windows, not open highways. The quantum-inspired traversable constructions tend to permit only small amounts of information or short-lived passage windows. The severity of restrictions comes from backreaction. Once you try to push more through, you change the geometry in ways that close the window or create instabilities. Preparation matters. Many proposals rely on extremely special initial quantum states, highly entangled, low entropy, or finely tuned. Those states aren't what you get from random astrophysical processes. If wormholes are ever natural, they would need a natural mechanism to create and maintain the special state, and no convincing mechanism is known. Those rules of thumb explain why wormholes remain tantalizing in theory, but evasive in practice. They also point the way toward useful research programs. Find realistic mechanisms that produce the needed quantum states, improve our understanding of quantum inequalities and backreaction, and search the sky for signatures that would falsify the most optimistic models. There's a final twist worth mentioning, because it speaks to why wormholes remain so compelling to physicists beyond the obvious sci-fi appeal. Wormholes force us to confront deep puzzles about information and black holes. Questions like what happens to information that falls into a black hole, and how does entanglement relate to geometry, have led to breakthroughs in quantum information approaches to gravity. Studying wormholes has helped clarify how entanglement entropy behaves in gravitational systems, how quantum error-correcting codes might underlie spacetime, and how constraints like energy conditions reflect information-theoretic limits. In short, wormholes act like a pressure test. Apply the idea to the most extreme cases, and you reveal tensions and connections in our theories that lead to real progress, even if the wormhole itself remains out of reach. To bring the ideas together in a more physical picture, imagine two conceptual vignettes side by side. In one, you have a classical Morris Thorne-style throat held open by some exotic matter you can place by hand. The energy requirements are huge, stability is precarious, and any matter you throw through tends to disrupt the throat. In the other, you have an entanglement-based wormhole. Two black hole-like systems prepared in a special quantum state, with a small interaction briefly making the bridge traversable for a delicate quantum signal. The first vignette appeals to bulky mechanical engineering and exotic materials. The second appeals to precise quantum state engineering and timing. Both are instructive, and both expose different faces of the same deeper problem: how to manage stress energy, stability, and causality in a theory that combines quantum physics and gravity. That collision of themes, geometry, quantum fields, information, and observational constraints, is why wormholes occupy a central spot in modern theoretical physics. They're not just a gimmick invoked to imagine faster-than-light travel. Instead, they're a versatile probe that forces us to sharpen our tools, reconcile apparently contradictory facts, and test the limits of our best theories. Whether they ever become practical devices, metaphors for quantum gravity, or purely theoretical artifacts, the study of wormholes has already advanced our understanding in ways that matter across several fields. We'll keep digging into the technical models, the limits imposed by quantum field theory, and the observational strategies that could give us a decisive hint one way or the other. Next up, a closer look at how specific semi-classical calculations handle quantum back reaction, and what those computations imply about the prospects for stable, macroscopic traversability. Okay, let's get into the guts of the problem. What happens when you stop treating spacetime as a fixed stage and let quantum fields push back on the geometry? That's the realm of semi-classical gravity, where Einstein's equations are sourced not by a classical energy density you can read off from a planet or a rocket, but by the average energy and momentum of quantum fields. Symbolically, the equation people write is G equals 8 pi t. The curvature on the left equals 8 pi times the renormalized expectation value of the stress energy operator on the right. The phrase renormalized expectation value is where most of the practical headaches live, because quantum fields in curved backgrounds are fiddly beasts. Think of quantum fields as a restless crowd of tiny oscillators filling space. Even in empty space they jitter, the vacuum fluctuations. In flat space, we normally subtract off an infinite background and say zero energy. In curved space or near boundaries, that subtraction is ambiguous and physical effects remain. The energy you measure can depend on the geometry or on how you set up the vacuum. The Casimir effect is the classic example. The plates alter which vacuum modes fit between them, and that change shows up as a measurable force. When you translate that intuition to gravity, those changes in vacuum energy show up as T and feed back into geometry. That feedback is backreaction. Why does backreaction matter for wormholes? Because a wormhole throat is a delicate balance. Classically, you already need stress energy that behaves in weird ways to hold the throat open. Once quantum fields are present, their fluctuations produce stress energy that can either help or hurt, and often the answer is hurt. Small fluctuations, or the average effect of many quantum modes, can concentrate near special surfaces in spacetime and produce large stresses that the classical solution never anticipated. Those stresses then change the geometry, sometimes catastrophically. The throat can pinch off, horizons can form, or singularities can develop where none were before. A big technical issue is computing T-ab in a given geometry. Unlike classical stress tensors, which come directly from known matter distributions, the renormalized quantum stress tensor depends on the field type, scalar, spinor, vector. The vacuum state you choose, there are multiple inequivalent vacua in curved space, and the method you use to remove infinities, regularization, and renormalization. In practice, exact calculation in full 3+1 dimensions for realistic wormhole metrics is impossible, except in very symmetric or lower-dimensional toy models. So physicists do a combination of analytic approximations, short-distance expansions, point splitting, numerical evaluations, and toy model studies in 1+1 dimensions where the math is tractable. What these studies often find is a pattern. If a geometry contains surfaces analogous to horizons or Cauchy boundaries, where information flow changes character, quantum vacuum polarization tends to pile up there. That piling up is sometimes finite and manageable, but in many cases it's divergent or grows without bound as you approach the critical surface. The physical picture is similar to piling sand onto a narrow bridge. The more you add, the more the structure shifts. For wormholes, the quantum sand affects whether light rays focus or defocus, and that determines whether the throat remains open. One canonical cautionary example comes from attempts to build traversable time machines out of wormholes. There, you not only ask for a spatial shortcut, but also permit closed time-like curves, loops in time. Semi-classical calculations tend to produce very large stress energy near the would-be time loop, because vacuum modes line up in pathological ways. Stephen Hawking argued this as his chronology protection conjecture. Quantum effects will grow and destroy any arrangement that would allow macroscopic time travel, preserving causality. It's not a proved theorem in full generality, but semi-classical analyses in many models show a runaway of the quantum stress energy that backreacts to remove the time machine before paradoxes can be exploited. Another classic result involves horizons and inner horizons of charged or rotating black holes. There, perturbations in the field can undergo infinite blueshift at certain surfaces, producing divergent energy densities. Similar potential blueshifts can occur in wormhole geometries when the causal structure causes signals to pile up. When that happens, T can blow up, and the semi-classical Einstein equation tells you the geometry will change dramatically. So designed or not, wormholes create many opportunities for quantum fields to misbehave. That's the discouraging headline, but the detailed story has finer shades. First, not all quantum stress energy is destructive. In special arrangements, quantum fields can produce controlled negative energy contributions, the same type of effect that opens a tiny traversable window in the Gauss-Jafferis wall construction. Second, the severity of backreaction depends on the state. A geometry may be stable in one choice of vacuum and unstable in another. That gives room for creative constructions. Choose the quantum state carefully, craft the coupling between fields or sectors, and the backreaction can be tamed or even used constructively. Of course, choose the state carefully is exactly the kind of demand that makes the scenario implausible for natural astrophysical systems, but it's perfectly legitimate as a way to map the space of possibilities. To make these remarks concrete, let's look at three types of semi-classical calculations that people use to test wormhole robustness. 1. Analytic short-distance expansions and energy conditions. Here the idea is to expand the renormalized stress tensor in terms of local geometric quantities, curvature, derivatives of curvature, and so on, and see whether those contributions are benign or pathological. Those expansions are well controlled at short distances and show generically that vacuum polarization includes pieces proportional to the curvature and to higher derivatives. If the throat's geometry forces certain curvature invariants to become large, the quantum corrections can become large too. That's a signal the classical solution is not self-consistent. You assumed a geometry and then discovered quantum fields produce energy densities that you didn't include. The remedy would be to solve the coupled semi-classical equations self-consistently, but that's usually hard. 2. Solvable lower-dimensional models. Many powerful insights come from 1 plus 1-dimensional toy universes, or from simplified models like the CGHS black hole or JT gravity. In lower dimensions, the renormalized stress tensor can often be computed explicitly and the full back reaction solved for. These models show both doom and hope scenarios. In some versions, vacuum polarization forms a naked singularity when you try to hold a throat open, killing traversal. In others, carefully prepared thermofield double states coupled appropriately, quantum corrections create a small window for signals to pass. These models don't prove anything about our 3 plus 1-dimensional world, but they illustrate mechanisms and pitfalls cleanly. 3. Numerical semi-classical studies. For some symmetric metrics, researchers compute T numerically for specific quantum fields in chosen states, and then integrate the semi-classical Einstein equations to see what happens. Those computations are heavy but illuminating. They can show a throat slowly tightening under quantum pressure, or they can demonstrate that a particular state yields a modest negative energy contribution that helps hold a throat open. A recurrent result is that to get a stable, macroscopic effect, you either need an enormous number of quantum fields, a large n-limit, or you must allow extreme parameter choices that are unlikely in nature. That mention of many fields deserves attention. Suppose you had not one quantized field, but 1,000 or 1,000,000 of them, all contributing similar vacuum polarizations. Then the net T scales with the number of fields, and you can amplify quantum effects dramatically. Some speculative discussions use this large N trick. If a civilization could somehow engineer many weakly interacting fields or species, they could boost the quantum negative energy available. It's an attractive loophole, but it introduces new problems. Large N tends to push you into a regime where the semi-classical approximation might break down in other ways. You could create large fluctuations, destabilize the vacuum, or run into unknown ultraviolet physics of quantum gravity. In short, many fields help numerically, but they shift the question rather than solve it fundamentally. Another useful concept that emerges from semi-classical studies is the quantum inequalities, or quantum interest, constraints. Ford and Roman developed formal bounds on how large a negative energy density a quantum field can produce, how long it can last, and over what volume. A vivid way to think about this is as an accounting rule. Negative energy is a loan from the quantum vacuum, and you must pay it back with interest. If you create some negative energy in one region, compensating positive energy must appear elsewhere, and the total energy fluxes must obey certain trade-offs. These rules make it hard to sustain macroscopic, long-lived negative energy regions. They also imply that attempts to exploit short windows of negative energy, for example, to create a transient traversable throat, are strictly limited in what you can accomplish. There are calculations that explicitly combine these quantum inequalities with backreaction. The picture that emerges is consistent. Fleeting small negative energy blips are allowed, and they can open narrow, short-lived channels for information. But once you try to push significant energy or mass through, the backreaction produces corresponding positive energy pileups that close the channel. In the gravitational language, sending a heavy spaceship through the throat changes the stress energy so much that the throat collapses or a horizon forms. That's precisely what many numerical perturbation studies show. Start with a wormhole geometry engineered to be marginally traversable if certain exotic stresses are present. Now perturb it by adding a finite flux of ordinary matter or a realistic probe. The linear perturbations grow into nonlinear changes. The throat pinches, curvature grows, and either a horizon forms or the throat snaps shut. The analogy I like is a soap film stretched over a wire frame. Small controlled tweaks let you shape the film, but slap it with a droplet of water and it deforms and might pop. Wormhole throats are like thin soap film handles in spacetime. Quantum and classical perturbations are the droplets and wind. There are also more constructive semi-classical examples worth describing because they show the counterintuitive direction quantum physics can take. In the Gauss-Jafferis wall construction I mentioned earlier, the setup begins with two black holes in anti-de Sitter, AD-S, space prepared in the thermofield double entangled state. Classically, they're connected by a non-traversable Einstein-Rosen bridge. Information can't pass from one exterior to the other. But if you introduce a small coupling that briefly connects fields on the two sides, a kind of engineered interaction, the quantum expectation value of the stress tensor develops a negative energy pulse that travels into the bridge and cancels the classical focusing just enough to let a low-energy signal get through. Importantly, the required coupling is tiny, the window is short, and the amount of information you can send is small. But the thing to notice is how explicitly quantum the mechanism is. The traversability hinges on entanglement plus a gentle classical coupling, not on stuffing classical exotic matter into the throat. People have reproduced similar qualitative effects in SYK models and other solvable many-body systems. Those studies are valuable because they map the gravitational intuition onto explicit quantum mechanical protocols. Entanglement resource plus coupling equals temporary channel. The results are robust in the narrow domain they address, but their relevance to macroscopic, astrophysical wormholes is limited. For one, these models often live in spacetimes with a negative cosmological constant, AdS, which behaves like a confining box. Our universe isn't AdS on large scales. It appears to have a small positive cosmological constant, and that difference matters for global causal structure, and for the availability of entangled states of the kind these toy constructions exploit. Semi-classical studies also expose a subtle but important point about horizons versus throat openings. A classical traversable wormhole must avoid event horizons at the mouths. You don't want a one-way door. Quantum effects can create local negative energy that helps with that, but they can also create new horizon-like behavior if the stress energy piles up incorrectly. For example, vacuum polarization near a would-be throat can produce a region where outgoing modes are suppressed, effectively creating a temporary horizon and preventing traversal. So quantum fields are double-edged. They can make a throat traversable in tiny ways, and they can make it impenetrable by forming horizons. All of this feeds into stability analyses. The standard approach is to consider small perturbations about a candidate wormhole solution and track their evolution, either analytically or numerically. In classical analyses, you check for modes that grow unbounded, signaling an instability. Semi-classically, you need to include the linearized quantum stress energy induced by the perturbation, and see whether that induced stress damps the perturbation or amplifies it. Too often the feedback amplifies it. The perturbation changes the vacuum expectation values in a way that feeds the perturbation, a positive feedback loop. There are some engineered states where the feedback is negative damping, but they require careful preparation and often involve equivalent exotic resources. An instructive toy analogy here is electronics. If you design a circuit and then put an amplifier in the wrong place, a small fluctuation becomes a runaway oscillation. Stabilizing a wormhole is like building a feedback control system that senses distortions and applies precisely the right compensating stress energy to keep the throat geometry within bounds. That requires sensors, actuators, and control laws, but in our case the actuators must manipulate quantum fields and gravitational degrees of freedom. That's engineering at the edge of known physics, not just hard engineering. There's also the thermodynamic angle. Any macroscopic structure in a gravitational setting has entropy and energy flows associated with quantum fields. Black holes taught us that horizons carry entropy and temperature. Wormholes interact with quantum fields too and can, in principle, have thermodynamic properties. If a wormhole throat supports a dense flux of quantum radiation, it will radiate and absorb energy, and that energy flow affects stability. Semi-classical analyses often show that a throat supporting even a modest negative energy distribution must pay an entropy price somewhere else. The balance of entropy and energy must satisfy generalized second law-like constraints. These thermodynamic considerations add additional restrictions on what states are available and which of those states are stable. You can see now why many serious researchers treat semi-classical backreaction as the decisive test for any wormhole proposal. It's one thing to write down a classical metric that looks like a tunnel. It's another to show that quantum fields in that geometry don't assemble into a destructive pattern. So far, semi-classical tests have been discouraging for macroscopic, long-lived traversable wormholes, unless you accept highly engineered quantum states or huge numbers of fields. They are more encouraging for microscopic, short-lived effects. Tiny windows for information, quantum teleportation analogs, or special lab-controlled many-body systems that mimic aspects of traversability. But the narrative is not purely negative. The semi-classical frontier has also produced constructive ideas that are worth emphasizing because they show physics pushing the boundary of what's allowed. One direction is exploiting boundary conditions and geometry to produce controlled negative energies, the Casimir idea scaled up conceptually. If you could design a throat interior with boundary conditions that strongly suppress vacuum modes inside relative to outside, you generate negative energy in the throat. In practice, that requires materials and configurations that we can only dream about today. boundaries that affect gravitationally relevant modes over macroscopic volumes. Another direction is engineered coupling between entangled systems, the Gauss-Jafferis wall-style trick, but scaled up and optimized. Theoretical work asks, can you design many-body protocols that produce larger effective negative energies without runaway back reaction? So far the scalings are discouraging, but the question is active. A related, promising idea is using quantum error-correcting codes and ideas from holography to think about robustness. In holographic toy models, geometry is emergent from quantum entanglement in a way that resembles a code protecting information against errors. Might the same code-like structure be used to shield a wormhole throat from destabilizing fluctuations? That's speculative, but it's an example of how cross-fertilization between quantum information and semi-classical gravity can open fresh routes. Even if those routes don't lead to macroscopic tunnels, they may teach us new ways quantum matter organizes in curved space and how to mitigate destructive back reaction in other contexts. Another practical lesson from semi-classical work is that not all purported wormhole signatures depend on macroscopic traversability. Quantum back reaction can leave observational fingerprints even when no human-sized tunnel exists. For instance, vacuum polarization around a would-be throat could change the accretion flow, create narrow spectral features, or produce transient bursts as the throat responds to matter falling in. Observers looking at compact objects might detect anomalies consistent with semi-classical effects rather than classical wormhole engineering. That means combining theory and observation is essential. We must translate sophisticated semi-classical calculations into astrophysical observables. Let's touch on chronology protection once more, but now from the semi-classical angle. Suppose you could arrange wormhole mouths to produce time offsets, the way you try to make a time machine. Semi-classical calculations typically find that vacuum fluctuations near the formed closed time-like curve grow without bound as the chronology-violating region forms, producing enormous T that, once fed back into the geometry, prevents the formation of the time loop. The mechanism is, loosely, that light rays that loop near the would-be closed world line can undergo infinite blueshift and lead to divergent energy densities. This offers a physical route for Hawking's conjecture. Quantum fields resist causal pathologies by becoming violent and altering the geometry. Again, these are not universal theorems, but they're compelling calculations in many models. What about numerical estimates? People often ask, how much negative energy would you need? And semi-classical work gives the sobering answer: enormous, unless you accept extremely peculiar states or configurations. Back-of-the-envelope estimates vary with throat size, desired transit time, number of fields, and tolerated tidal forces, but the numbers scale badly. A throat wide enough for a person may need exotic energy equivalents comparable to planetary or stellar masses, or enormous numbers of quantum fields arranged in precise states. Those numbers come from combining the classical geometric constraints with quantum inequality bounds on negative energy. If you try to cheat by packing negative energy into a smaller volume, tidal forces or curvature invariants explode and destroy anything trying to pass. Before leaving semi-classical back reaction, it's worth highlighting one technical success. In certain carefully chosen settings, researchers have solved the semi-classical equations self-consistently and produced geometries that include quantum corrections rather than treating them as small perturbations. Those solutions are often in lower dimensions or in the presence of a large number of fields, but they are vital proof of principle calculations. They show unambiguously that quantum fields can smooth out singularities, can produce small negative energy regions that change causal structure, and can, in special circumstances, render classically forbidden behaviors allowed for modest scales of information transfer. The moral is that semi-classical gravity is rich enough to alter qualitative behavior. You can't a priori assume quantum fields are negligible. They can be the decisive factor, for better or worse. All this brings us back to a practical perspective. Semi-classical analysis is the crucible that tests wormhole ideas. It's where hopeful classical metrics are either validated or shown to be inconsistent when realistic quantum effects are included. So far, the tests favor microscopic, short-lived, or highly engineered traversable effects, not robust, macroscopic tunnels you can drive a ship through. That doesn't make the subject dull, quite the contrary. Semi-classical work has tightened our understanding of energy conditions, generated new techniques for computing renormalized stress tensors, and sparked connections with quantum information that illuminate how space itself might emerge from entanglement. Next, the conversation naturally moves toward two directions: how to translate these semi-classical insights into potential observational tests, and how laboratory analog systems can let us probe similar backreaction effects in a controlled environment. Those avenues let theory confront data and experiment, and they show how even negative semi-classical results point to concrete things we can look for with telescopes and tabletop setups. We left off with semi-classical gravity as the decisive test for any wormhole idea. When you let quantum fields push back on the geometry, the results are often harsh. The natural next step is to ask how we can turn those theoretical insights into things we can look for. What would a wormhole actually do to light and matter in the sky? How could we mimic wormhole-like behavior in the lab? And what new theoretical directions might change the verdict? Those are the practical lines of attack: search, simulate, and refine theory. Each one chips away at the unknowns in a different way. Start with observations. If even a handful of macroscopic wormholes existed within reach of our telescopes and detectors, they would probably give themselves away in several distinct ways. And the trick is to know what to look for, because the signals won't all be dramatic smoking guns. Some will be subtle deviations from the black hole or star templates astronomers use every day. Others could be anomalous transient events that don't fit known astrophysical categories. Gravitational lensing is the oldest and cleanest test. Anything massive bends light, and a wormhole mouth is no different in principle. But the details are peculiar. A star, a planet, or a normal compact object produces familiar lensing patterns: multiple images, magnified brightness, and Einstein rings when alignment is perfect. A wormhole mouth can do those things too, but with twists. If light rays can pass through the throat and emerge from the other side, the lensing map between source and observer can have additional images or characteristic brightening that doesn't fit simple mass models. For example, light that goes partly through the throat and partly around it can produce phantom pairs of images or ring-like features with unusual intensity profiles. Surveys that monitor millions of stars for microlensing, the temporary brightening when a compact object passes in front of a background star, are a natural hunting ground. People have run analyses asking, if a population of small wormholes existed, how would the microlensing statistics look? So far, the data have been consistent with ordinary compact objects, which means large populations of easily detectable wormholes are unlikely. But rare or cleverly disguised mouths could still be hiding. That's why improved surveys keep tightening the net. Direct imaging of compact objects is another avenue. The Event Horizon Telescope gave us the first resolved image of material behavior close to a supermassive compact object. If some candidates are wormhole mouths rather than black holes, the brightness distribution and shadow region could differ. A black hole has an event horizon, a one-way membrane that swallows everything, and that leaves a characteristic imprint on the surrounding light. A wormhole mouth, lacking a true horizon, can let some light through and reprocess radiation differently. The exact differences can be subtle because the environment, accretion disks, magnetic fields, turbulent plasma also molds the image. Still, as imaging sharpens, we'll have better statistical tools to say whether any observed shadow deviates from black hole predictions in a way that points to exotic geometry. Gravitational waves opened an entirely new window. When LIGO and Virgo detect the merger of two compact objects, the waveform encodes their internal structure. Black holes have very specific ringtone frequencies determined only by their mass and spin. Those are the familiar tones a struck bell emits. If one of the merging objects is exotic, a wormhole mouth, a boson star, or some other compact but horizonless configuration, the post-merger ringtone can carry additional features. People talk about echoes in the ringtone, small, delayed reverberations that arise if part of the waveform reflects off an inner structure instead of being swallowed by a horizon. Some analyses of early data claimed hints of echoes, but successive studies showed those hints were marginal at best and could be artifacts of noise. As detectors improve, though, echo searches will become more decisive. Space-based detectors in the future will probe different frequency bands and longer duration signals, offering a complementary handle on exotic compact objects. Fast, bright transients like fast radio bursts, FRBs, are another intriguing possibility. FRBs are millisecond-long flashes of radio waves from cosmological distances, and their origins are still debated. If a wormhole mouth suddenly interacts with a compact parcel of plasma, or if compact objects traversing mouths produce shocks, those events might look bursty. Additionally, lensing by tiny wormholes could split an FRB into multiple closely spaced pulses. Detecting the telltale time delays and frequency-dependent signatures could flag a lensing event by a compact exotic object. The observational challenge is separating exotic lens signatures from complex propagation effects in the interstellar and intergalactic media. Pulsar timing is a particularly sensitive probe for certain types of perturbations. Pulsars are incredibly precise clocks. Even tiny changes in the gravitational potential along the line of sight show up as timing residuals. A passing wormhole mouth, or gravitational waves emitted by interactions of mouths, could imprint distinctive signatures on pulsar timing arrays. Those arrays are already hunting for stochastic gravitational wave backgrounds from supermassive black hole binaries. Someday they might also constrain or detect anomalous signals consistent with exotic compact objects. There are also more indirect but powerful constraints. If a wormhole mouth were surrounded by an accretion flow, the spectral energy distribution, how bright it is at different wavelengths, could diverge from black hole expectations. For instance, the absence of an event horizon can change how infalling matter radiates as it piles up or passes through. Similarly, the statistics of X-ray variability from candidate compact objects could reveal unusual behavior. High-resolution spectroscopy, long baseline monitoring, and multi-wavelength campaigns are essential to tease these effects out of messy astrophysical environments. All of these observational hunts share a common difficulty: degeneracy. Many exotic signatures a wormhole would produce can be mimicked by more mundane astrophysics, complex accretion dynamics, magnetic field reconnection, or unusual distributions of matter. This is where multi-messenger astronomy becomes crucial. Combining electromagnetic observations with gravitational waves, neutrinos, and timing data narrows plausible explanations. If you see an unusual lensing event that also lines up with odd gravitational wave behavior and an FRB echo, the case for something truly exotic becomes stronger. Parallel to sky surveys are lab-based analogs. These are not wormholes in the gravitational sense. You can't fold space in a tank, but they mimic key mathematical features of wave propagation in curved backgrounds. Why do this? Because analogs let you test dynamical and stability questions in a controlled setting. How do waves behave near throat-like regions? How robust is a tunnel to perturbations? What kinds of transient effects show up when you tweak the effective geometry? Those experiments have produced surprising and useful results. A class of analogs uses metamaterials and transformation optics. In these setups, engineered materials bend electromagnetic waves precisely the way a curved geometry would bend light. The same mathematical description that tells you how light moves in a curved spacetime can be implemented as a spatially varying refractive index. That led to demonstrations of electromagnetic devices that route fields between two regions in ways reminiscent of a wormhole connection, at least for certain components of the field and over certain frequency bands. One notable example is an electromagnetic wormhole device that guides magnetic fields between two isolated regions while remaining nearly invisible to external probes. These devices don't alter spacetime. They simply control Maxwell's equations in ordinary space to imitate some geometric features. Still, they're powerful proof-of-principle platforms for wave dynamics and for testing ideas about shielding, mode conversion, and how an engineered throat responds to incoming signals. Acoustic analogs, water channels, shallow water flows, or Bose-Einstein condensates, BCS, simulate horizon-like behavior for sound or collective excitations. The most famous of these experiments aim to mimic Hawking radiation, the quantum emission predicted at black hole horizons. In a BEC, researchers have made setups where fluctuations in the condensate behave as if they are propagating in a curved effective spacetime, and measurements have seen thermal-like spectra suggestive of Hawking-like processes. Those experiments don't create real gravitational black holes, but they give empirical support to the mathematical machinery we use to reason about quantum fields in curved backgrounds. Extending those experiments to throat-like analogs, where waves must traverse a narrow region linking two reservoirs, is an active area. They let physicists study scattering, mode conversion, and back reaction in ways that inform semi-classical calculations. Superconducting circuits and traption systems provide another avenue. They are flexible quantum simulators. Certain many-body Hamiltonians that people use to model black hole analogs, including the SYK model mentioned earlier, can, in principle, be approximated in laboratory quantum simulators. That's a long-term enterprise, but if you can prepare states that mirror highly entangled thermofield doubles and then engineer couplings between them, you can emulate the entanglement coupling tricks that produce tiny traversability in toy gravity models. Doing this in a lab would not produce a spacetime tunnel, but it would test the information-theoretic protocols and the dynamics that gravity-mapped calculations rely on. It would also bridge theory and experiment directly. We could watch how quantum resources permit or deny the transfer of information in systems that are computationally and conceptually close to the gravity setups. There's an important complement to lab analogs: numerical simulation. Because exact semi-classical calculations in full 3+1 dimensions are hard, sophisticated numerical relativity and quantum field theory computations become critical. People run simulations that couple classical geometry to approximated quantum stress energy sources, explore perturbative regimes, and look for instabilities. These studies have become increasingly realistic, including effects like rotating mouths, magnetic fields, and matter flows. They don't yet produce a fully convincing macroscopic wormhole that remains stable under all reasonable perturbations, but they have clarified where the precarious points lie. In practice, the combination of analog experiments, numerical simulation, and astronomical observation is a powerful triangle. Each approach checks and constrains the other two. On the theoretical front, new developments in quantum gravity and quantum information theory have recast wormholes from mere geometric curiosities to central actors in how we think about spacetime itself. Two examples illustrate how wormholes influence modern thinking in deep, sometimes surprising ways. First are the replica wormholes that entered the black hole information conversation in the late 2010s. When people tried to compute how the entropy of radiation emitted by a black hole evolves over time, naive semi-classical calculations predicted an ever-growing entropy, implying information loss, the famous black hole information paradox. Newer calculations using gravitational path integrals and replicas, essentially making multiple copies of the system to compute entropy, found that surprising gravitational saddles that look like wormhole connections between replicas contribute to the entropy in a decisive way. These replica wormholes, Change the result so the radiation's entropy follows the page curve expected for a unitary quantum system. The entropy rises and then falls, consistent with information ultimately being recoverable. The technical details are complex, but the punchline is conceptually simple and profound. Wormhole-like configurations, even if they don't correspond to traversable tunnels in spacetime, are essential ingredients in how gravity organizes information. That means wormholes are not just sci-fi bridges, but mathematical players in the deepest questions about quantum gravity. Second is the broad ER equals EPR idea and its offspring in holography. The picture that entanglement patterns can be read as geometric connectivity has motivated a flurry of work showing that many properties of spacetime, distance, connectivity, even aspects of locality, can arise from how quantum degrees of freedom are entangled. From this angle, wormholes are the geometric avatars of particular entanglement structures. This line of thinking has practical payoffs. Techniques from quantum information theory, error-correcting codes, complexity measures, entanglement wedges, have become useful tools for studying gravitational dynamics. They've helped produce clearer statements about what kinds of geometries are physically consistent and how information is encoded in or escapes from gravitational systems. Even if this research doesn't give us macroscopic traversable tunnels anytime soon, it's reshaping how physicists approach the deep problems that wormholes expose. Those advances also feed back into observability. If wormholes are important for how information is encoded, their influence might appear indirectly in phenomena such as late-time correlations in gravitational wave signals or subtle statistical anomalies in high-energy astrophysical processes. That gives experimentalists more specific patterns to hunt for and theorists more constrained models to calculate. We should also return to primordial and microscopic wormholes. If macroscopic, long-lived tunnels are hard or impossible, perhaps tiny wormholes were baked into the early universe and left small but detectable imprints. Primordial wormholes could, in principle, lens the cosmic microwave background, contribute to non-Gaussianity in primordial fluctuations, or seed unusual compact objects that later appear as dark or anomalous lumps. Searches for compact dark matter candidates already constrain some possibilities. Continued improvements in CMB measurements, gravitational wave backgrounds, and microlensing surveys will tighten those constraints further. If primordial wormholes exist primarily at Planckian scales, the tiny foam John Wheeler imagined, they won't be directly observable, but they could still inform the structure of quantum gravity and the behavior of entanglement at microscopic scales. All of this suggests a balanced research program. On the observational side, keep pushing gravitational wave sensitivity, refine microlensing and pulsar timing analyses, and combine multi-messenger data to break degeneracies with ordinary astrophysical processes. On the experimental side, build analogs in metamaterials, BECS, and quantum simulators to study wave dynamics, stability, and information transfer in controlled throat-like settings. On the theoretical side, sharpen semi-classical computations, explore large N and many-field tricks cautiously, and pursue the quantum information perspective that has been so fruitful recently. None of these paths guarantees a wormhole you can travel through, but each can either discover signs of exotic structures or narrow the theoretical possibilities until we have a clearer verdict. It's worth emphasizing, as a final practical point, why this is more than academic curiosity. The same tools developed to analyze wormholes, advanced numerical relativity, techniques for computing quantum stress tensors, methods to prepare and probe highly entangled quantum states, have broad applicability. They improve our ability to model extreme astrophysical environments, to design quantum devices, and to reason about information in physical systems. So whether wormholes end up being cosmic highways or subtle quantum artifacts, the scientific work inspired by the question pays off in many directions. If you find yourself wanting to imagine a future civilization that does harness wormholes, the realistic roadmap is instructive. Such a civilization would need an ability to manipulate quantum fields and stress energy at enormous scales, to control topology in a deep quantum sense, and to build monitoring and active stabilization systems that tame the notorious backreaction effects. It would be as much an achievement in quantum engineering and spacetime control as anything else, closer to mastering quantum gravity than to any engineering feat we currently know how to do. That's not a petty qualification. It's a recognition of where the key obstacles sit. Mastering energy and geometry at that level would revolutionize physics in ways we can barely imagine. So what should you take away? Wormholes are real in the sense that our best equations allow their existence, and that quantum physics gives surprising ways to soften classical no-go arguments. But the barriers are steep. Enormous or cleverly organized negative energy, delicate quantum state requirements, and destructive backreaction all stand in the way of human-sized, stable, traversable tunnels. Observations so far have not revealed obvious wormhole mouths, but they continue to test the possibilities with increasing rigor. Laboratory analogs and quantum simulations let us probe the dynamics and information-theoretic aspects in controlled settings, improving our intuition and our computational tools. And new theoretical advances, from replica wormholes to entanglement-built geometry, show that wormholes already play a role in how physicists think about the deepest puzzles of gravity and quantum mechanics. That mixed tantalizing mathematical possibility, stubborn physical obstacles, experimental searches, and conceptual payoffs, is precisely why wormholes keep pulling people back into the problem. They force us to bring together the sharpest tools of general relativity, quantum field theory, quantum information, and observational astrophysics. Whether wormholes ever become practical highways or remain profound theoretical probes, the journey of studying them is teaching us a lot about the universe and about the limits of what is physically achievable. Keep watching the skies, the labs, and the theory papers. Progress may well come from a direction no one currently expects. Keep watching the skies, the labs, and the theory papers. Progress may well come from a direction no one currently expects. To make that a bit more concrete, let's walk through what the immediate next steps actually look like. The experiments people can do now, the theoretical questions that are ripe for progress, and the kinds of discoveries that would genuinely change the story about whether wormholes could ever be more than clever math. First, the observational program. We already have tools that are directly relevant, and those tools are getting steadily better. Gravitational wave detectors like LIGO and Virgo have opened a new window on compact object mergers. Planned upgrades and next-generation detectors will widen that window and increase sensitivity. In practical terms, this means better ability to test whether merger remnants match the clean black hole templates predicted by general relativity, or whether they carry anomalies that hint at some exotic interior structure. The most concrete signature to look for in current data is ringed-on echoes, tiny, delayed reverberations after the main merger signal. If part of the gravitational wave reflects off an inner surface instead of being swallowed by an event horizon, you might see a repeating pattern of decaying echoes. The evidence for echoes so far is inconclusive and debated, but improved detectors and longer observation runs will settle the question more decisively. Meanwhile, very long baseline interferometry, the technique behind the Event Horizon Telescope image of MADI 7's black hole, will continue to sharpen our images of the regions around supermassive compact objects. If even a small fraction of these candidates were actually wormhole mouths, the brightness profile and the photon ring structure would depart in subtle but detectable ways from the black hole predictions. That's not a single dramatic signal. It's a suite of differences in shadow shape, photon trajectory distributions, and time-variable emission that multi-wavelength campaigns can test. The important point is that astronomy is now precise enough to push tests of exotic compact objects into a serious, data-driven phase. Microlensing surveys and pulsar timing arrays provide additional complementary probes. Microlensing looks for the transient brightening of background stars caused by compact objects crossing the line of sight, Wormhole mouths could produce distinctive light curves or produce multiple, time-offset images that betray a throat. Pulsar timing arrays, which track the ticks of millisecond pulsars across the galaxy, are exquisitely sensitive to gravitational perturbations and will be a natural way to search for passing compact objects or unusual gravitational wave backgrounds that ordinary black hole populations don't explain. In short, the observational toolkit is strong and getting stronger, and each new dataset tightens the net on where wormholes, if they exist, could be hiding. Second, the experimental analogs and quantum simulator program. The beauty here is that you don't need to build a literal tunnel through spacetime to test the core physics questions. Metamaterials, optical waveguides, Bose-Einstein condensates, and superconducting quantum circuits can all emulate key mathematical elements of throat-like geometries or horizon physics. For example, experiments have already reproduced Hawking-like thermal emission in analog setups. Extending that program, researchers are actively designing laboratory systems that simulate two-region connections and study how waves, classical or quantum, scatter, get reflected, or transmit through effective throat regions. Those tabletop experiments are invaluable because they let us probe stability, mode mixing, and the interplay between boundaries and fluctuations in controlled ways. If a lab analog shows that a certain class of instabilities is unavoidable in any throat-like system with certain properties, that insight translates into constraints on gravitational wormholes as well. There's a second experimental front with an information theory flavor, building and testing the quantum many-body protocols that correspond to traversable wormholes in toy models. The SYK model and its cousins have been central in theoretical developments because they are solvable and share key features with black hole physics. If quantum simulation platforms, trapped ions, cold atoms, or superconducting qubits can realize SYK-like couplings or thermophile double-like entangled states, then researchers can experimentally turn on couplings between the two sides and watch whether controlled information transfer occurs in the way gravity-inspired calculations predict. Again, this won't produce a macroscopic tunnel, but it will test the deep idea that entanglement plus carefully engineered interaction can act like a channel across an emergent geometric connection. Demonstrating these protocols at scale would be a milestone. It would show the quantum mechanical skeleton of a wormhole-like channel is physically realizable, even if gravity refuses to cooperate at human scales. Third, the theoretical and computational path. There's a concrete, practical agenda here that researchers are pursuing. One major goal is to push semi-classical calculations further. Compute the quantum stress-energy T-AB in increasingly realistic wormhole-like backgrounds, include relevant fields, scalars, fermions, gauge fields, and solve the back-reaction problem self-consistently whenever possible. Advances in numerical relativity, coupled with better approaches to renormalization in curved backgrounds, make that program more feasible than it was a decade ago. If a self-consistent semi-classical solution existed in 3+1 dimensions with manageable quantum corrections, it would be a breakthrough. Conversely, if carefully executed semi-classical work rules out large classes of traversable solutions that will be just as powerful, it would narrow the theoretical landscape and sharpen the kinds of exotic matter or quantum mechanisms we would need to look for. Closely connected is progress on quantum gravity itself. Wormholes sit at the places where our two great theories, quantum mechanics and general relativity, fight to be reconciled. Developments in string theory, loop quantum gravity, and other approaches, especially where they connect to holography and quantum information theory, are reshaping expectations about topology change, the emergence of spacetime, and the role of entanglement. The replica wormhole calculations that helped resolve aspects of the black hole information problem are a prime example. Objects that look wormhole-ish at the level of the gravitational path integral turned out to be essential for understanding how information is encoded and recovered. That suggests a healthy possibility. Even if macroscopic traversable wormholes are forbidden, wormhole configurations might still be essential internal elements of quantum gravity, with observable consequences. The theoretical challenge is to elevate these ideas beyond toy models and special spacetimes, to understand how robust they are in geometries that resemble our universe. Fourth, the search for new forms of matter or novel field dynamics. The most obvious bottleneck for macroscopic traversability is the need for exotic stress energy that violates classical energy conditions. That raises a clear practical question. Are there permitted field theories or new states of matter that naturally produce negative energy densities of the right sort without spectacular instabilities? The Casimir effect shows negative energy exists in principle, but it's tiny. Researchers explore more exotic possibilities: scalar fields with non-standard kinetic terms, forms of vacuum polarization in strongly curved backgrounds, or even topological defects like cosmic strings that change how geometry behaves. Any experimental hint of such matter, whether in high-energy experiments, condensed matter analogs, or unexpected astrophysical behavior, would dramatically alter the landscape. That's why particle physics experiments, cosmological observations, and condensed matter discoveries all feed into the wormhole question indirectly. What kind of discoveries would genuinely change the conversation from interesting math to maybe feasible someday? Here are some clear, high-impact possibilities. Detection of an astrophysical object whose observational signatures cannot be reconciled with any known compact object model, something that lensing, imaging, and gravitational wave data all point to as horizonless but compact and stable. That would be the single biggest empirical clue that exotic compact objects exist and may include wormhole mouths. Laboratory demonstration that many-body quantum systems can robustly implement the traversable channel protocols from the SYK/thermofield double family, and that the capacity of those channels can be scaled up significantly. That would show the information-theoretic skeleton of traversability is physically achievable and suggest new ways quantum fields might be manipulated on large scales. Discovery of matter or field dynamics that allow sustained, macroscopic negative energy densities without catastrophic instabilities. Whether this comes from particle physics, emergent condensed matter phenomena, or a breakthrough in field theory, it would be the single most direct way to bridge the gap between the tiny Casimir effects we can measure and the planetary-scale exotic energy budgets some wormholes seem to require. Theoretical breakthroughs showing topology change is physically permitted in a controlled way at low energies, or that spacetime emergence from entanglement leads naturally to macroscopic connectivity under realistic conditions. That would rewrite the rulebook and potentially show new routes to making wormholes stable and usable. Each of these is a high bar and none is guaranteed. Still, they're concrete, testable milestones. The scientific program makes progress whether or not any wormholes are eventually harnessed. Better tests of gravity, improved gravitational wave catalogs, refined quantum simulators, and deeper understanding of quantum field theory in curved backgrounds are all valuable outcomes. It's worth pausing to consider practical engineering issues people sometimes gloss over when they imagine wormhole technology. Suppose, purely hypothetically, a civilization figured out how to make or find a traversable mouth and stabilize it. What would come next? The first challenge is placement and anchoring. If mouths are mobile, they must be parked and secured to avoid wandering in ways that produce unpredictable time offsets or dangerous tidal interactions with neighboring matter. If mouths are fixed but widely separated, you need to get to them. That requires sending probes through interim space or developing ways to move mouths by controlled energy redistributions. Both tasks imply mastery over large energy flows and precise control over geometry. The second challenge is the interface. The junction between local space and the throat must be gentle enough to avoid ripping apart whatever enters. That means the geometry and the matter distribution near each mouth must be tuned to match ordinary space in a way that keeps tidal forces low. In practice, This is a non-trivial design problem. The throat must transition smoothly from near-flat regions into the narrow passage and back again. It's the sort of structural engineering that, in ordinary contexts, would be routine, but here the materials you get to use are quantum fields and gravitational degrees of freedom. Third is traffic control and safety. If wormholes enabled fast travel or communication across distant regions, you would need a rulebook for access to avoid collisions, destructive interference, or dangerous causal configurations. The possibility of time offsets makes this especially thorny. Moving a mouth at relativistic speeds can desynchronize clocks and, in principle, create closed time-like curves. Any practical wormhole network would have to ensure that time offsets are controlled or prohibited, which again requires a deep dynamical understanding of how mouths evolve and interact with surrounding matter and fields. Fourth is the energy budget and maintenance. Even if negative energy could be arranged temporarily to flux open a throat, maintaining that configuration against inevitable perturbations and the constant rain of cosmic radiation would consume resources. Active stabilization, constantly sensing the throat's geometry and applying compensating stress energy, implies running an enormous control system that manipulates quantum fields. From the standpoint of present physics, that's not just advanced engineering. It's a mastery of quantum gravity, or at least of semi-classical control at enormous scales. Those practical hurdles suggest a likely pattern if wormholes ever become usable. They will appear not as cheap shortcuts, but as high-capital, restricted access infrastructure used by advanced societies that have mastered unusual physics. Think of them like international space elevators or fusion reactors, tools that transform transportation and communication, but require massive resources, long-term maintenance, and centralized control. It's also important to take seriously the ethical and societal questions. Suppose a civilization could alter spacetime topology or open time offset connections. Who controls that power? What governance structures and safety regulations would be needed? The risk of causality-related paradoxes, even if ultimately suppressed by physics, would reshape philosophical and legal thinking. Those are not purely speculative concerns. Any large-scale technology that fundamentally changes how we move or communicate raises questions about equity, security, and unintended consequences. Scientists and technologists would be well advised to think about these issues early, even if the technology is speculative, because the frameworks for responsible research and deployment are useful across many advanced technologies. Now let's come back to one of the most commonly asked questions. Could wormholes be an engine for time travel? The short answer is, they're a plausible ingredient in time travel thought experiments, but every careful analysis suggests that nature has ways of preventing paradoxes from being exploited at macroscopic scales. The mechanics are straightforward. If you desynchronize the clocks at two mouths, by moving one at relativistic speeds, for example, then entering the younger mouth could, in principle, lead you to emerge from the older mouth at a time earlier than your entrance. That creates closed time-like curves and the classic paradoxes. But in all the semi-classical calculations done to date, quantum effects blow up as you try to create such configurations. Vacuum fluctuations pile up, stress energy diverges, and the would-be time machine is destroyed or altered before it becomes usable. That evidence supports Hawking's chronology protection intuition. The laws of physics conspire to keep macroscopic, exploitable time travel out of reach. That's not a proof that it's impossible in absolute terms, but it's a compelling reason to think that any civilization that tries to build a time machine will encounter a wall of quantum and gravitational fireworks. All of this still leaves room for two interesting caveats. The first is scale. Most of the compelling quantum negative energy effects and traversable channel constructions work at microscopic or information-theoretic scales. It's fully possible that wormhole physics plays an essential role in quantum gravity and information flow at the Planck scale, or in the encoding of black hole microstates, without ever yielding macroscopic tunnels. That would be a huge conceptual discovery about the nature of space and information, even if it leaves human travel unchanged. The second caveat is surprise. Physics history is full of discoveries that rewrote expectations. Superconductivity, lasers, positive energy theorems, dark energy, and quantum teleportation all emerged in ways many did not expect. It's always possible that some novel quantum field, an unanticipated phase of matter, or a fresh insight into topology change will shift the conversation dramatically. That's why a balanced research program, combining theory, observation, and experiment, is the smartest route. You don't need to bet the farm on building a wormhole to benefit from studying them. The techniques and insights generated by this research have broad utility across physics and technology. If you want to follow this field as it develops, here are practical ways to keep track without getting lost in hype. Read the observational results from gravitational wave and imaging collaborations with a skeptical but curious eye. Watch for repeated, robust deviations from black hole templates before drawing exotic conclusions. Pay attention to peer-reviewed demonstrations of traversable channels in quantum simulator platforms. Those are the experiments that will teach us how entanglement and engineered couplings can be harnessed. Follow semi-classical studies that compute T-ab in candidate geometries. If those studies become more comprehensive, they will be the deciding factor for many theoretical proposals. And finally, stay tuned to developments in quantum gravity and holography. The most revolutionary conceptual progress is likely to come from new theoretical understandings rather than incremental engineering tricks. To return to the intuition we started with, the folded paper trick, that mental picture remains useful. Wormholes are not magic. They're geometric features the equations of gravity allow. The challenge is turning the toy trick into a real, sustained, usable shortcut in a world governed by quantum fields and energetic constraints. We've learned a lot. The math is generous. Quantum physics gives both obstacles and loopholes, and observations and experiments are closing in on testable predictions. The most honest current assessment is that traversable, human-scale wormholes are far from our reach given what we know, but wormhole research has already reshaped how physicists think about space, time, and information. That reshaping matters. So what's the final, practical takeaway? Keep paying attention, but with calibrated expectations. Wormholes are real in the sense that they exist as consistent, if exotic, solutions to Einstein's equations and as essential ingredients in some quantum gravity calculations. They're speculative as engineering projects for now because they demand resources and control we don't possess, and because quantum effects tend to block macroscopic causality-violating constructions. But the story is not settled. Observational surprises, laboratory breakthroughs in quantum many-body control, or theoretical revolutions in our understanding of space and topology could change the picture. Until then, studying wormholes remains one of the clearest and most productive ways to probe the intersection of gravity, quantum mechanics, and information. It's a question that forces us to refine our tools, question our assumptions, and occasionally to fold the paper a different way.